Imagine this. We humans have been broadcasting radio waves into the deep void of space for over a century. Satellites and telescopes have been our eyes and ears, reaching far beyond the confines of our atmosphere, seeking not just to explore but to question, are we really alone? Despite these efforts and the vastness of the universe, which is brimming with billions of galaxies, each housing millions of stars and potentially even more planets, we have yet to receive a definitive answer. This silence raises a profound question known as the Fermi Paradox. With such high probabilities and possibilities, where are all the aliens?
The universe is a grand stage of cosmic activity, with star formations, planetary systems, and habitable zones playing pivotal roles in the potential emergence of life beyond Earth. The rate at which stars form, the distribution of planets around these stars, and the specific conditions within habitable zones collectively shape the probabilities of life. Yet the silence in our search for extraterrestrial communication suggests a perplexing contradiction between our expectations of a universe teeming with life and the stark reality of our solitude. Astrophysical models provide us with a framework to predict where conditions might be ripe for life. However, the intricacies of these models often reveal that the conditions necessary for life as we know it are incredibly complex and perhaps rare in the cosmos. This complexity not only deepens the Fermi Paradox, but also enhances the scientific rigor needed to understand it. The exploration of these astrophysical factors involves a delicate balance between the known laws of physics and the vast, often unobservable phenomena occurring across galaxies. This exploration not only challenges our understanding of the universe, but also our place within it. As we peer into the cosmos, we are continually reminded of the greater complexities and mysteries that govern our cosmic neighborhood.
Recent advancements in exoplanet detection have revolutionized our understanding of the cosmos. Techniques such as the transit method, radial velocity method, and direct imaging have uncovered thousands of exoplanets, many of which lie in the so-called habitable zone of their stars. This zone, where conditions may be right for liquid water, a crucial ingredient for life as we know it, has been the focal point of intense scientific study. The search for biosignatures, or signs of life, on these exoplanets involves detecting atmospheric composition that could indicate biological processes. For instance, an excess of oxygen or methane could suggest the presence of organic life forms. However, interpreting these signs is not straightforward. Abiotic processes can also produce similar biosignatures. Thus, the challenge lies in distinguishing between living and non-living chemical processes from millions of light years away. This pursuit not only expands our knowledge of the universe, but also reframes the Fermi Paradox. Each discovery of a potentially habitable planet increases the odds of not being alone in the universe. Yet, the continued absence of clear extraterrestrial signals only deepens the mystery.
The concept of galactic habitable zones, GHZ, is pivotal in understanding the distribution of life in the Milky Way. These zones are regions in a galaxy where conditions are just right for life to potentially arise and sustain. Factors such as the density of stars, the frequency of potentially catastrophic cosmic events, and the distribution of essential elements form the backbone of these habitable zones. Studies suggest that regions too close to the galactic center pose higher risks from supernovae and gamma-ray bursts, which could sterilize life on any nearby planets. Conversely, areas too far from the center may lack the necessary chemical elements that are crucial for the development of life. Therefore, the GHZ is typically a ring-shaped area located at an optimal distance from the galactic center. Understanding these zones helps us pinpoint where to look for signs of life in the galaxy and provides a framework for interpreting the silence we encounter in our search for extraterrestrial intelligence. This analysis not only brings clarity to the Fermi Paradox, but also guides future astronomical endeavors. The Anthropic principle and the rare Earth hypothesis offer frameworks to understand why intelligent life might be rare across the cosmos. These principles suggest that a series of extremely unlikely coincidences on Earth have created the perfect conditions for life, and such conditions may be exceptionally rare elsewhere. For instance, Earth's stable orbital path, its protective magnetic field, tectonic activity, and the presence of a large moon, which stabilizes its axial tilt, are all cited as critical factors. These conditions contribute to a stable climate and environment where complex life forms can evolve and thrive over geological timescales. The rare Earth hypothesis argues that planets with similar life-supporting conditions are scarce in the universe, thus providing a potential answer to the Fermi Paradox. This hypothesis emphasizes the complexity and fragility of the conditions necessary for life, suggesting that Earth might indeed be a rare gem in a vast uninhabitable cosmos.
The Great Filter Theory posits that at some point from pre-life to an advanced civilization capable of colonizing galaxies, there is at least one extremely hard step that almost all life fails to overcome. This theory provides a framework to understand the apparent absence of observable extraterrestrial civilizations and could be seen in catastrophic events that prevent the emergence or long-term survival of advanced life. Events such as asteroid impacts, supervolcanic eruptions, or nearby supernova could have the power to wipe out emerging civilizations. However, the filter might also include self-inflicted catastrophes such as nuclear war, uncontrolled artificial intelligence, or devastating climate change. Each of these events has the potential to halt the progress of a civilization, or even lead to its total extinction. Understanding these filters helps us grasp the precarious nature of our existence and might offer insights into the survival strategies of potential distant civilizations. It also explains part of the Fermi Paradox by suggesting that while life might be common in the universe, the emergence of advanced life capable of interstellar communication might be exceptionally rare.
The vast distances between stars are a formidable barrier to the exchange of information or physical travel. However, technological advancements could potentially bridge this cosmic gap. Radio signals, despite being the most traditional form of interstellar communication, suffer from dispersion and the need for immense power to be detectable over interstellar distances. Alternatives like laser transmissions offer more directed and thus stronger signals over these vast distances. Advanced civilizations might also utilize megastructures such as Dyson spheres to harness the energy of entire stars, providing them the power necessary for interstellar communication. These speculative technologies provide intriguing possibilities for communication, but they also raise questions about detectability and feasibility considering our current understanding of physics and technology. The exploration of these technologies not only expands our understanding of what might be possible, but also provides a sobering reminder of our current limitations in the cosmic arena. This realization is central to our understanding of the Fermi Paradox. The silence in the cosmos could be a sign not of the absence of life, but of the monumental challenges that interstellar communication presents. The search for extraterrestrial intelligence, or SETI, has been an ongoing effort to detect signs of intelligent life beyond Earth. This initiative primarily uses radio telescopes to listen for unusual signals from the cosmos that could indicate the presence of technologically advanced civilizations. Optical SETI, another branch of this search, tries to detect signals in the form of brief pulses of laser light. These efforts have been both inspiring and frustrating. While they have significantly advanced our capabilities in radio astronomy and signal processing, they have yet to yield conclusive evidence of extraterrestrial signals. The lack of results has not dampened the spirit of researchers. Rather, it has fueled further questions and theories around the Fermi Paradox. Future prospects for SETI include more sensitive detectors, broader search spectra, and more comprehensive sky coverage. Each advancement brings a renewed hope that perhaps in the vast silence of the cosmos, we might one day detect a whisper of life beyond our lonely planet. The simulation hypothesis presents a radical yet intriguing explanation for the Fermi paradox. It posits that our reality might be a simulation,
an intricate digital construct overseen by an advanced civilization. Under this hypothesis, the silence of the cosmos could be a programmed aspect of our particular simulation, designed to isolate us or to simplify the complexity of a universe teeming with life. Philosophically, this hypothesis touches on fundamental questions about the nature of reality and our perception of existence. If true, it would imply that the universe and its laws are not what they seem, and that our efforts to understand them could be fundamentally flawed. While the simulation hypothesis is more of a philosophical conjecture than a scientific theory, it provides a unique lens through which to view the Fermi Paradox. It encourages a broader exploration of reality, perception, and the limits of human understanding. The decision to send messages into space, known as active SETI, involves significant ethical considerations. While the primary goal is to establish contact with extraterrestrial civilizations, such actions carry potential risks. One major concern is the possibility of attracting attention from a hostile civilization, potentially endangering humanity. Furthermore, interstellar messaging raises questions about the rights and autonomy of other potentially sentient beings in the universe. Are we justified in attempting to alter or influence other civilizations, potentially disrupting their natural development? These ethical considerations require careful deliberation among the global community. The debate encompasses not only scientists and policymakers, but also the broader public, as the implications of contact would extend to all of humanity. This discussion is crucial in framing our approach to the Fermi Paradox and our ongoing search for cosmic companions.
The Fermi Paradox is not merely an astronomical question, but a multidisciplinary puzzle that spans astrobiology, philosophy, sociology, and even futurology. Integrating insights from these diverse fields enriches our understanding of why we might seem alone in the universe. Astronomy provides the tools to search for planets and life, while astrobiology speculates on the nature of life that might exist.
Sociology offers perspectives on how civilizations might develop or collapse, influencing their ability to communicate. Philosophy questions the underlying assumptions we make about life and intelligence. By weaving together these diverse strands of human knowledge, we can form a more comprehensive picture of the Fermi Paradox. This synthesis not only deepens our understanding, but also highlights the profound complexity of our quest to find not just any life, but intelligent life that mirrors our own capacity for reflection and curiosity.
In conclusion, the Fermi Paradox remains one of the most intriguing mysteries of our time. Through astrophysical analysis, technological exploration, philosophical inquiry, and ethical debate, we continue to probe the depths of this cosmic silence. Whether the answer lies in the rare nature of life, the vast distances of space, or perhaps in realms of reality we have yet to understand, our journey through these cosmic mysteries not only teaches us about the universe, but also about ourselves. As we gaze into the cosmos, we hold a mirror to our own existence, our ambitions, and our place within the vast, starry expanse. The Fermi Paradox presents one of the most profound questions in the cosmic arena. With billions of stars in our galaxy alone, many of which host planets in their habitable zones, why is the universe so eerily silent? Where are all the advanced civilizations we expect to find? This paradox strikes at the heart of our understanding of the universe and our place within it. It challenges the assumption that the emergence of life, and particularly intelligent life, is likely given the right conditions. As we delve into the realms of astrophysics, astrobiology, and interstellar communication, each discovery and hypothesis adds layers to our understanding, and yet, the great cosmic silence persists, deepening the mystery.